All right, so this is the slide we left off with. And actually, I added a slide, and I meant to print it off, but the printer didn't work for me. So you guys don't have this slide. But we last talked in here about like things that are kind of faux sciences, like astrology, numerology, ufology, all things that I just find kind of interesting. But the reason they aren't sciences is kind of summarized on this board here. So like, for instance, if it is, this is how this works. Okay, you kind of see the three circles kind of directed into the word science. If it is science, for instance, then it will rely only on natural causes. Okay, so some of these things aren't necessarily natural causes, like your faith. Now we can talk about. I'd be glad to talk outside of class about my faith. I'm not an atheist. I am a Christian and all that. So your faith is not a science, okay? It is very real, and to me, it's a mover and a shaker, but it's not predictable. It's not a science. So another thing, if it's a true science, you can test it, okay? Remember, we said the scientific method is you, based upon observations, you come up with a hypothesis. That's your best guess, okay? And you test it. If it's a science, you can test it. Let's see, what's the third one? Progresses through creation and testing models of nature that explain the observations as simply as possible. There's something called the KISS, keep it simple, stupid. Okay, so science has to be kind of straightforward. It can't be like crazy complicated. The most simple model or explanation you can come up with, if that explanation fits the observations, then that's the right explanation. Okay, so those are kind of hallmarks of science. Okay, so continuing on. The thing about science is about experimentation, and one of the things is if you run an experiment, you need to be able to describe that experiment, and people need to be able to, in different parts of the world, run the same experiment. So you measure quantities, and people need to measure the same quantities. Okay, this world, this earth we live on, is pretty small, and it's gotten smaller since technology and people travel and scientists share information. Okay, so we definitely have to standardize. This is my point. We need to standardize how we measure stuff. So here actually are the international ways of measuring things. Like if you wanted to measure mass, okay, internationally speaking, you would use the kilogram. Okay, if you want to measure length against the metric system, you would use a meter. I brought a meter stick here today. If you wanted to measure temperature, it would be Kelvin, units of Kelvin. If you wanted to measure like how many little pieces there are, it's the mole, which is a big number. Electrical current, it's the ampere. Time, it's the second. Luminosity, it's the candle. So those are all kind of like, so scientists can speak amongst each other. So can you kind of picture like way back in the 200 AD, 200 AD, think of kind of the clusters of kind of budding scientists and think of maybe their different ways of measuring things. Okay. So that's the international standard units. Okay. So international-wise, we definitely go with the metric system. Length was meter, okay, instead of feet or inches. Mass was kilogram instead of pounds or that sort of thing. So metric is the way we go. And so you need to know your way around a little bit the metric system. Now, this is a very busy slide. You're like, oh my gosh. You're probably familiar with metric prefixes, okay? Here's one for you. Which is bigger, a meter or a centimeter? How many people think it's a meter is bigger? Yeah, okay, very good. Which is bigger, a gram or a kilogram? How many people think it's a gram? How many people think it's a kilogram? Kilogram's bigger. I know, you're like, what? Actually, there are 4 metric prefixes that I think you need to know, okay? 4 metric prefixes, and here they are. One of them is larger and two of them are smaller. So I already told you a kilogram is bigger, a kilogram is bigger than a gram. And as it turns out, a kilogram is 1,000 times a gram. Now, the other three are smaller. So you were thinking that a meter is bigger than a centimeter, and you're right. The word cent, how many cents are in a dollar? 100. Yeah, 100 cents in a dollar. There are 100 centimeters in a meter. Okay, so that's why this is how this goes, or one way it goes. We can say that the prefix centi means 1/100th. Okay, 1/100th of x, x being kind of what we call the base unit. So if we were going to come up with what we call like an equals statement, we could say that 1 centimeter, cm, because the abbreviation for centi is c, 1 centimeter is equal to 1/100th of a meter. That's how that goes. What's the abbreviation for kilo? You guys know? Very good. Kilogram is kg. Abbreviation for just the regular old kilo is K. Perfect. Okay. So if I draw a line right here, the ones I want you to know, kilo means more than the base unit, 1,000 times the base unit, and centi, milli, and micro means smaller than the base unit. So the way this works over here, let me go ahead and kind of refer you to this little chart over here. So we talked about kilo, we talked about centi, okay, and here is milli. Milli is 1,000th of. So I'll go ahead and write that 1 over 1,000 times x. So if we were going to kind of write an equals statement, we could say, let's see, let's go with grams. So we could say 1 milligram, cute little milligram, is equal to 1/1000th of a gram. Any questions about that? Oh, I see. I'm looking over here on this little table that I brought in. That's not right. This little M next to micro. I don't know why they did that. Well, maybe some people do that. But it really should be, the symbol for micro is actually, it's mu. It looks like a U with a tail on the front end. That's mu. That's micro. And it is 1/1,000,000th. So I'm going to go 1 over 1,000,000. So 1 over 1,000,000. 1, 000, 000. 1/1,000,000th of something. So micro is very small. If I write an equal statement, let's go with liters. So I can go 1 microliter. 1 microliter is equal to 1/1,000,000th. 1 with 6 zeros after it, liters. So of all of those prefixes, those are the 4 that I think will kind of might pop up here and there. Okay, any questions? All right. So, you brought your calculators today because I want to talk about using your calculators in scientific notation. Just a little bit, I know. Right? How many people have used scientific notation here and there, been exposed to it a little bit? Okay. Scientific notation is a good way of taking a really big number and making it so you can understand it, or a really small number and making it so you can understand it. Because like this number right here, the 12, 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, that's like too many zeros. Yeah. So we could pack that up in scientific notation. And small numbers get kind of irritating too, with all of those leading zeros. We can pack both of those up in scientific notation. So the deal with scientific notation is what you do is you find the decimal, okay, and you move the decimal, okay, either to the left or the right, whichever way you need to do it. And you move it so that you get a new number that is between 1 and 10. You move it so you get a new number between 1 and 10. That number, after moving the decimal, is called the coefficient. That's going to be your first number in your packed up scientific notation number. Then what you do is you write down your coefficient, you write the times, and then you write the number 10, and then the little superscript of 10, the exponent of 10. Is the number of places you had to move the decimal to get your decimal number coefficient. Okay, so we're gonna have some practice at this. One last thing down here at the bottom is if you packed up a large number like that first number up there, okay, if you packed up something like that, then your power of 10 is going to be positive. Okay, if you packed up something that is small, something like this, okay, then the 10 raised to a power, that power is going to be negative. If it's big, that power of 10 is positive, and if it's small, that power of 10 is negative. So let's see how we do. Okay, so either together or on your own, let's pack this one up. So what I tried to describe before is, where's the decimal in this number? Seems like it's, yeah, at the very end. I agree. So I'm going to go ahead and put the decimal there at the very end. Cool. Now I'm going to have to move it to the left, right? I get my left and rights mixed up. So I'm going to go 1. I'm going to count the number of spaces. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. I'm going to move it 10 places. And so my decimal number is going to be 1.23. That's my coefficient, times 10 raised to the 10th. It's going to be the positive 10th, isn't it? I don't usually put a positive there, but it is positive 10. Does that work for you? Okay. The next one? We have big numbers over here on the left and small numbers over there on the right. So in this case, decimal again is at the end. We move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it goes between the 5 and the 9. Move it in 11 places. So now the coefficient is 5.9145 times 10 to the 11th, I think. I think it's just good that you know if you see a number packed up in scientific notation and it's times 10 to the 11th, you're like, oh, well, that's a pretty big number. All right, this one's not so big. Again, the decimal is there at the end. We move it 1, 2, 3. That's it, right? 3 places. Packed up, it's 4.3 times 10 to the 3rd. Next one. Moving the decimal that's over at the end. So 1, 2, 3, 4, 5. Move it over 5 places. So it's between the first one and that 0. So it's 1.01 times 10 to the 5th.
Why couldn't you just leave the decimal after the first initial 10 since it's the 0.1? So it would be like 10.1 times 10 to the power of 4.
Because the coefficient needs to be less than 10.
Plus,
Yeah, that's a good question, though. She was wondering, could we go with 10.1 times 10 to the 4th? But that coefficient would be larger than 10. Just a little bit larger, not much.
yeah. And I'm used to just like rounding down too, so that might be it.
Yeah, it could be. Now, small numbers. How about this one? There, you know where the decimal is. So in this case, we're going to have to move the decimal to the right. I got 1, 2, 3, 4, 5, 6, 7, 8, 9 places. And that gives me 4.721 times 10 raised to the 9th power. But what do I have to do to the 9? Make it negative, exactly. 4.721 times 10 to the negative 9. Looks like we're all good with that. Let's see this one. Next one, let's see, 1, 2, 3, 4. Looks like I'm moving it 5 places to make it 5.006 times 10 to the negative 5th. This one, move it 1, 2, 3, 4 places to give me a 3.3 times 10 to the negative 4th. And last but not least, this one, which it's weird to pack this one up in scientific notation. It's almost more trouble than it's worth. But if we do it, we go 1, 2 places. So it's 3.57 times 10 to the negative 2. Does it work? Yeah. Okay. Now, get your calculators handy. So go ahead and take out your calculators. I brought 2 today. I brought the one, like the programmable calculator, TI 86, and then like one that's not programmable. So here's the deal. Let's see. The first number you enter is going to be the coefficient. Okay, so to enter a number in scientific notation, let's just kind of practice. Enter this number in scientific notation. How about 6.32 times 10 to the 11th? Okay, 6.32 times 10 to the 11th. So what we're going to do is enter 6.32. I hope everybody's calculators they're coming out with new things, so is what I'm used to. 6.32. Press whatever key you need to enter to do scientific notation. So it's either your EE key, your EXP key, or your SCI key. Press that. For me, it's EE. And you should kind of see it kind of give a, in my case, it gave me the letter E, but sometimes it gives you like a little place over there where it's ready for your scientific notation. And then press 11. Okay. If this were negative, and we're going to do some examples here in a minute, if this were negative, I would push 11, and then I would hit my, my plus minus key. Not my subtraction key, but my plus minus key. And we'll have some practice at that in a minute. So just for kicks, if you don't mind, go ahead and take that times 25. Hit your times key, 25. Let's see if we all get the same answer. Okay. So what I got was 1.58 And you should look around there somewhere and see that you see like a 13 somewhere there. Good. That 13 means that as you write it, that's times 10 raised to the 13th power. How'd we do? Okay. I can't tell. Did everybody get it? Fish? Did yours work? Score. Oh, your calculator. Oh, yeah. Oh, such a cool calculator.
How did you do that?
Okay, so here's your E. So you're going to put in 6.32. And then, yep. Second E. Perfect.
And then
11. And then times 25.
Oh, okay. So we don't even have to put like the 10 in, do we?
Right. No.
Oh, yeah.
Yeah,
Okay.
yeah. When you hit the EE key, that's like putting the 10.
I got you. Okay.
Perfect.
Thank you.
Did yours work out okay? Yay. Okay. Very good. Did yours come out okay too? Oh, yeah.
There you go.
Awesome. Very good. So, yeah, once you have it entered in using that EXP key or the SCI key or the whatever key, once you have it entered in as a scientific notation number, then it's just like any other number. All right. Looks good. Okay, so let's do some together now. I haven't done these in my calculator, so I'll be doing them too. Right off the bat, you see two numbers in parentheses. They're both scientific numbers, numbers packed up in scientific notation. Now, if you see two numbers in parentheses, that means that they are multiplied by each other. I don't know, maybe you already knew that. That's to say that you're going to take 4.56 times 10 to the 7th times 6.7 times 10 to the 12th. That's what my parentheses mean. So let's see how we do this. See if we can get the same number. It's kind of like balancing your checkbook. Like if you get one number and you're uncertain if you did it right, you just do it again and see if you get the same number. And if you don't, I don't know what to say. Aren't calculators, they just feel fun. I like calculators. All right. I'm going to do a little bit of rounding, and I'll kind of tell you about rounding here in a minute. How we doing? Did you guys get the same? Is that up there? That was good. Yeah. Piece of cake.
Do that, right?
Excellent. Bless you. Did yours come out okay too?
Yeah.
Heck yeah. Awesome. They come out okay?
Yeah.
Okay. Excellent. Are there any questions? I can't tell. It's looking like it's coming out okay. Oh, he's already got his others done. Did yours come out okay? Good. So, yeah. Okay, so yeah, go ahead and do the others. But I do have one thing to say before I move on. Notice that I went ahead and I wrote what my calculator displayed. That's the calc number. And then I wrote a rounded number under that. This semester, I'm not gonna, your textbook does a good job of talking about how you round according to significant figures. I'm not gonna emphasize that too much, but I did round correctly in that, just in general, can you see where I had 3 digits here? I had 2 digits here. So notice in my answer, I rounded it to 2 digits. Okay, just in general, kind of get in that habit. And there's a reason behind all of that, correctly rounding. If you don't round correctly, put another way, I'm not going to count it wrong. But just don't give me too many numbers. Okay, so you guys did the other ones. Let me see, I didn't do them. Can somebody help me out? What's the answer to the second one? Someone be brave. 1 point.
20 or 1.7 times 10 to the negative 20.
Awesome.
right?
1.7 times 10 to the negative 20th. I'm thinking I saw that number other places. What do we think? We like it? Excellent. Okay, what's the answer to the, thank you, what's the answer to the next one? Be brave.
2.2 times 10 to the negative 34.
Awesome. Thank you, sir. Is that what everybody else got too? Sweet. And do you see why they rounded the way they did? Just because there were, let's see. Well, in this one, I guess we could have, in this second one, I guess we could have gone with 3, but that's okay. I would definitely, this is very good. And in this one, we had to go with 2.
So you just take whatever is the smallest out of your equation and round it to that number?
Yep,
Okay.
truncate it off. And if it's a 5, you round up. So, you know, we're just going to kind of work on it this semester. I'm not going to, but in my chemistry classes, that's something else. This is good. Any questions? Sweet. How are we doing for time? Okay, so this is your first assignment, and just right before I came to class, I did get this as an assignment in that WebAssign, which I have 1 student enrolled already, so that's good. WebAssign, remember, is that online thing you can do, and it's looking like the WebAssign is going to be very similar to this, which is good. The WebAssign, the online thing, is very similar to your paper and pencil questions you need to answer. The other thing about WebAssign so far is I can only get it due, like, it's open now through Friday. And what I really kind of wanted was to turn it in on Monday, so I decided how to do that. So if you're using WebAssign, if you don't mind having it done by the end of the day Monday, that would be great. Any questions about WebAssign? I'm going to show it to you here in a minute. You're like, what the heck? And I checked that already told you, but in the bookstore, the textbook is $100 instead of $200. But it looks pretty good. Sorry, I didn't mean to. I haven't
It's
seen one
weird that
open.
it's not connected.
It is weird, it's not
I
bound.
don't like that.
It is less expensive than bound.
Right. I feel like I could lose everything if I didn't have that.
Yeah. I see some shaking of heads. Are you gonna go try the WebAssign thing?
Probably.
I'll show you what that looks like. So this will be due Monday.
So do we just do that on just like a sheet of paper or something?
Yep, just do it on a sheet of paper, yeah. Yep. So this is what it looks like in WebAssign. It's got a mind of its own. We are gonna go into chapter 2 here in a minute, so. Okay, so open student view.
It's not actually on your screen if you're expecting it to be.
What's that?
It's not up here if you're expecting it to be.
Thank you. Direct. Why? Oh, this one's. Yay. Okay. So are we good? Can you find this in your, notes? Any questions about the homework assignment due Monday?
Will you say what they are again?
Oh, sure.
I have it written down.
Page 23 and 24, short answers, questions 1, 2, 19, and
So 11, 2, 19, or 21.
21.
Very good. Thank you. Did everybody else get the assignment? Okay. All right. So, so now we're finally getting into a little bit more of the physics part of it. One of the things that physicists look at are how things move, okay? How things, what their velocity is, how much energy they have is kind of related to how fast they're going. Something that's going fast has more energy, right? It kind of intuitively figures that. But one of the things just kind of basically with motion is I think it's interesting to think back way back when, and they used to think like if an object, like if this chair goes, it's here now, okay, and I come back in later and the chair is over there, okay, what they used to think was, well, good chance that was magic. You know what I'm saying? They didn't equate that somebody had to use a little bit of energy to physically, with a force, push that chair over there. You know what I'm saying? They just thought things just kind of, but that's kind of the unnatural sort of things that they used to think about, okay? So now what we know, when I move that chair from there to there, okay, I could have lifted it, okay, and moved it over, I had expended some energy. I could have pushed it over, applied some force. Trying to think, if I lifted it, okay, and expended some energy, I'm lifting it up against gravity. Will we talk more about gravity? Okay. I am applying a force to the chair and letting out place to move the chair. So with regard to forces, and in physics, I kind of picked some of the hot topics. We should know a little bit about forces. We aren't going to know everything there is to know about forces. Okay? But a force can be a lift, a push, a pull, that's a force. Okay? Some forces are more obvious than others. Some forces you can see, some forces you can't. Forces don't necessarily result in something moving. We are all held here as you're sitting at your chairs. a force is working on you to hold, force of gravity is holding you on the earth, okay? So force, we talked about scientists need to be able to, across the world, talk intelligibly about these certain quantities, including force. So actually the international, it uses, this is what people use. Newton's is the unit of force. Newton is a unit of force. There are other units of force, but Newton is the preferred unit of force in science. Notice that Newton can be broken down into those SI units. Remember the SI unit for mass is kilogram. The SI unit for length is meters. We'll talk about how do you look at a force and break it down into kilograms and meters. Okay, of course the SI unit for time is seconds. That's what S stands for. Okay, so a Newton actually can be broken down to kilogram meter per second squared. So examples of forces, again, pulling and pushing, the force of gravity, the force of friction that basically slows things, okay, the rubbing sort of friction. Wind is a force. Wind is air moving from one location to another. Now, in astronomy, we talk about these four forces that are present today that needed to be present if they're present today in our universe, at some point they were created, or they were always here. So these are what we call the four fundamental forces. And if I were to ask somebody on the street, when you think of forces, what do you think of? Probably these aren't necessarily what the average person would think of on the street. So for instance, the first two forces, fundamental forces in the universe, are very small. So we'll be talking in our chemistry section kind of how an atom is put together. But an atom is a crazy thing. An atom should not be. Okay? So in order to keep an atom together, it needs the strong force, and I guess I jumped the gun, the strong force and the weak force in order for an atom to stay together. Electromagnetic force you might be kind of familiar with. If you take two magnets and you have North Pole and North Pole next to each other, they will repulse each other. The same thing if you take two negatively charged particles, they will repulse each other. Okay, that's electromagnetic. Those examples of electromagnetic force. And of course, there's the force of gravity. So those are the four fundamental forces. Two of them involve atoms. These two involve atoms. Okay, and the other two work on a larger scale. Electromagnetic and force of gravity. All right, so back to something a little more practical. Oftentimes there's more than one force acting on an object at the same time. Happens all the time. If that's the case, or I guess I'm going to show you, if that's the case, we say the overall forces are additive, and the overall force is what we call the net force. So here in a minute, I got a picture of tug of war down at the bottom. But a net force is basically adding the different forces that are working together. It's like an addition problem, really. So with forces, what works well oftentimes is we can use these arrows to indicate forces. Notice that in these three arrows, if you call them arrow A, arrow B, and arrow C from left to right, okay, and they all represent forces. Which force is the greatest? How many people think A is the greatest force? How many think B is the greatest force? How many people think C is the greatest force? Exactly, because it's little, we call those vectors, is longer. So that works pretty well. Sometimes it's kind of fun. I've seen, well, when I took physics, you can actually take these little things and cut them out and kind of line them up to each other and actually understand what the net force will be. You add them together. Okay. Which force looks like it's the smallest and going in a northwest direction? Is it A? Is it B? Yeah. B looks like it's the smallest, kind of going that way. Did I say northwest? I meant northeast. How about northeast? Very good. So we can use vectors to describe forces. So an example of a net force at work Notice in this case, we have two groups of people on either side pulling with a particular force, okay? In this case, you know, we got these people pulling F1, we got these people pulling F2, and as they're written with the same lengths, okay? And they're pulling opposite directions, so it's a wash. So actually, this is a net force of 0. Okay, so not so much in the next figure. Okay, so I don't know how well you can see it, but down here, they're showing that these guys over here pulled more. Oops, go back. Their little vector is longer. They pulled more, so that does have a net force going in that direction. I mean, it makes sense, right? So forces are a player in physics. Can't remember what they call that. Branch of physics. Switching gears now, okay, and actually, I think we've got time to kind of get through this last topic. One of the things that's helpful, leaving force for now, going back to just motion, an object moving, like moving the chair from position A to position B, one of the things that's important is to be able to talk about how fast that happens, or its speed, okay? So if you wanted to know how fast something's moving, you basically take the distance it moved and the time it divided it by the time it took to get that distance. So these are all kind of intuitive. So let's do this right quick. This example. Let's call this over here position A, and call this one over here position B. And so for the overall, for the time, I know it's broken into time segments of 1 second, but let's go for the full enchilada, okay, and come up with its speed. So all we got to do is speed, or average speed, is equal to the distance it went. How far did it go?
80 meters.
80 meters. I agree. Is that, you buy that? I do too. It went 80 meters, and how long did it take it?
10 seconds.
I see your point. I think in this case, I think it's 4 seconds. They're saying, they're showing you at second interval 1, second interval 2, second interval 3, or second interval 4. So time interval. So we don't add those together. So this is when your clock, this is when your clock says 0 seconds. This is when your clock says 1 second. This is when your clock says 2 seconds. It's the same clock, 3 seconds, 4 seconds. So I'm liking the 4.0 seconds. I can almost do that math in my head. All right, so 80 divided by 4 is 20?
20 meters per second.
Yeah. That's it. Any questions about that? That's its average speed. Okay. Pretty good. So just a few things are kind of my hints when I think about working science problems. That includes physics and chemistry problems, maybe astronomy problems. We're not going to do any problems in astronomy. But draw pictures from the text of the problem you need to work. Feel free to bring in equations. Like what I could have done on the previous one was to bring in, speed is equal to, maybe I did do that, is equal to distance divided by time. Okay. Rewrite any key equations, rewrite the numbers from your problem. It just kind of helps hit you overhead with it. Now, those first 3 are optional. This is not optional. Okay, so the last 2 you have to do when you work problems in this class, okay? So get in the habit of always including the units. So in the problem we worked before, we made sure that we put meters and seconds. Those were our units. So make sure you do that as you work the problem and on your final. So, and then the other thing is if you, even if you think it in your head, you can think it in your head, but you also have to write it down. So you have to kind of show the logic of how you work the problem. Okay, so show all of your work. That's not optional. That would be on your homework and on the test. Okay, so I know it's like, how could we have an assignment after that? But you have an assignment after that. These will give you a chance to drag your calculators out. These are also due on Monday. They're just kind of like we just did, given a distance and a time, okay? So on page 49, in the problem section, questions 6, 8, and 10. And if you've had a chance to look at what your author does, it's kind of cool. He brackets, so like right above 6, there's question 5, and you have the answer to question 5. And question 5 is very similar to question 6, okay? And I'm pretty sure if you do use WebAssign, you also can, they give you hints with WebAssign too, so I hope you try WebAssign. I think it's like fun. Okay, any questions? Those are both due on Monday.